Hello guys, welcome to DEY'S learning. It is part 3 of atomic structure chapter. In today's session, we will cover the following topics. Number 1 is ionization energy of hydrogen and hydrogen-like systems. Number 2 is the energy difference and the difference in radius between the successive Bohr orbits. Number 3 is Debug Equation. Number 4 is atomic spectra of hydrogen. And number 5 is the advantages and limitations of Bohr's atomic model. So get ready with your copy and pen. Without wasting any time, let's get started. Now our today's first topic is ionization energy of hydrogen and hydrogen-like systems, right? In our previous lesson, we have learned that the energy of the Bohr orbit are represented by E1, E2, E3, E4, etc. And these energies are negative energy, and the energy of the electron when it is present at the infinite distance, that is r equal to infinity, the energy of the electron is equal to 0, right? So ionization energy is the energy required to remove this electron from first orbit to infinity. So we can write the ionization energy of hydrogen atom, that is IE, this one is equal to energy of infinity minus the energy of first orbit, that is infinity minus E1. Infinity is the energy of the energy of the electron when it is present at the infinite distance from the nucleus, right? So it is infinity minus E1, and this is nothing but 0 minus, and this is the energy of the first orbit of hydrogen atom. As we know from our previous lesson that this value is nothing but minus 13.6 electron volt, right? So this one is equal to positive 13.6 electron volt. This is the ionization energy of hydrogen atom. So look at the value very carefully, that this value is just equal in magnitude with the energy of the first orbit of hydrogen atom. But the energy of the electrons in its Bohr orbit is negative, and the ionization energy's value is positive. This is the only point of difference, but the magnitude are equal. So from this relation, we can also calculate the energy of the ionization energy of other hydrogen-like systems. So we can write the ionization energy of other hydrogen-like system, that is the monoelectronic system, the system which contains just one electron, like as we know He plus, Li2 plus, etc. We can write ionization energy IE, this one is equal to, as it is infinity minus En, okay, when the electron is present in the nth orbit. And as we know, it is infinity 0 minus, and the value of En, as we know, this one is equal to E1 into Z square by N square, right? Okay, so this one is nothing but minus E1 into Z square by N square, and this value of E1 is minus 13.6 electron volt. So this is minus of minus 13.6 electron volt into Z square by N square. Okay, so therefore this ionization energy is nothing but positive 13.6 into Z square by N square electron volt. Okay, this is the value of ionization energy of all other hydrogen-like systems. ओके, डिफरेंट कॉम्पिटिटिव एग्जाम्स में ये क्वेश्चंस बहुत बार पूछा गया है कि फाइंड द आयोनाइजेशन एनर्जी ऑफ Li2 प्लस when the electron is present in the first excited state. Now the first point to note is that the first excited state. So as we know, first orbit is the ground state, and E2, this is the second orbit, it is the first excited state, right? This is the ground state, this is the ground state, this is the ground state for any monoelectronic system, and it is the first excited state. First excited state. This is the first excited state. First excited state means E2. This is the second excited state. This is the third excited state, and so on and so on. Okay. So the first excited state means N equal to 2, right? So the ionization energy, this one will be equal to the energy of infinity minus E2 for Li2 plus, right? And as we go in the similar manner, we can find that the ionization energy value, this one is 13.6 into for Li2 plus, Z is 3, so this is 3 squared divided by the second excited state, it is 2 squared. This one electron volt, this one is 30.6 electron volt, right? Okay. So this is the ionization energy value of Li2 plus when the electron is present in the first excited state. Now we have come to our second topic. It is the difference of radii and energies between two successive Bohr orbits. We actually want to compare between the radius of different Bohr orbits. This is the first orbit. This is our first orbit. This is n equal to 1. This is our first orbit, that is K orbit. This is L orbit, this is n equal to 2. This is our third orbit, M orbit, this is n equal to 3. This is our fourth orbit, that is n equal to 4, right? Now we want to compare the radius and energies of these different orbits. Look, this is very important. Now in the general expression of radius, from the general expression of radius, we know Rn equal to R1 into n square by z. Okay, as we know from our previous lesson. So for hydrogen atom, we can write this z equal to 1. So for hydrogen atom z equal to 1, so we can write Rn, this one is equal to R1 into n square. Okay, this is our relation for hydrogen atom. Now when for the first orbit, this n equal to 1, so this is the radius of first orbit, R1. For the second orbit, this n equal to 2, so this R2, this one will be 4 into R1. For the third orbit, n equal to 3, so R3 equal to 9 into R1. For the fourth orbit, it is n equal to 4, so R4 equal to 16 into R1. So look at here very carefully that as we go further from this nucleus, rate of change of this radius is increasing. So this difference is of 3 into R1. We can write from here the difference R2 minus R1, this one is equal to 3 into R1, right? The difference between the third orbit, the radius of third orbit and second orbit. So we can write R3 minus R2, this is equal to 9 minus 4, this is 5 into R1. The radius of fourth orbit and third orbit, the difference in radius between fourth orbit and third orbit, this is R4 minus R3, this is equal to 16 minus 9, this is 7 R1. So as we go further from the nucleus, the difference in radius is increasing. If we consider the energies of the orbits, look at here what we have found. The energy of the first orbit, this is 13.6 electron volt, and the energy of the second orbit, this is minus 3.4 electron volt. we have come to this conclusion from our general expression of energy. This is En equal to E1 into Z square by N square. Z square by N square, and for hydrogen atom Z equal to 1. So we can write for hydrogen atom En equal to E1 by N square. We can write this E1 by N square, right? This is the relation between the energy of first orbit of hydrogen atom and the other orbits of hydrogen atom. So this is the E1, this is 13.6 electron volt. For the second orbit, this is 13.6 divided by 4. For the third orbit, this is 13.6 divided by 9. For the fourth orbit, it is 13.6 divided by 16, and so on and so on. From this arrangement, we can say that the energy gap between the E2 and E1 is very large, and the energy gap between E3 and E2 is relatively smaller, and the energy gap between E4 and E3 is more smaller. The energy difference between E4 and E3 is further smaller, and as we go to the outer orbits, the energy difference becomes smaller and smaller. So as we go further from the nucleus, the difference in radius between the Bohr orbits increases gradually, and the energy difference between the successive Bohr orbits decreases gradually. So this is a very important idea. So the conclusion that we can draw from our discussion, that the difference in radius between the two successive orbits, that is R2 minus R1, it is less than R3 minus R2, and it is of course less than R4 minus R3, and it is less than R5 minus R4, and so on, right? So the difference of radius between the second orbit and first orbit is less than the difference in radius between third orbit and second orbit is less than the difference in radius between fourth orbit and third orbit, and so on and so on. And the energy difference between the second orbit and first orbit, that is E2 minus E1, this one is greater than the energy difference between the third orbit and second orbit, it is E3 minus E2, and it is greater than the energy difference between fourth orbit and third orbit, and it is greater than the energy difference between fifth orbit and fourth orbit, and so on. Okay, so as we move outwards from the nucleus, the difference in radii between the successive orbits increases gradually, and the difference in energy between the successive orbits decreases gradually, right? Today's third point is Rydberg equation. This is a very important equation to explain the atomic spectrum of hydrogen atom, right? We will derive Rydberg equation, but before that, we must have some important idea about two important terms, that is wavelength and wave number, and the relation between the two terms. Let us consider a wave like this. Say a wave is propagating in this manner. Okay, right? 1, 2, 3, 4, 5. Nice. Okay. Now suppose this length is 1 meter, right? This length is 1 meter. Okay. Within this 1 meter length, how many complete oscillation of the wave occurs? This is oscillation 1 up to this one. This is oscillation 2, 3, 4 and 5. So there are 5 complete oscillation occurs within this unit length of 1 meter, right? So the number of complete oscillation made by the wave within unit distance is known as wave number. It is known as wave number, and it is denoted by nu bar. Okay. So what is wave number? The number of complete oscillation of the wave occurs within unit length or unit distance, it is known as wave number, right? In this example, what we have assumed, the value of nu bar, this one is equal to 5 per meter, because there are 5 complete oscillation of the wave occurs within the distance of 1 meter. But actually in practice, this value of nu bar is much greater than that. It is actually in the order of say x into 10 to the power 7 per meter. In reality, the value of nu bar occurs in this order of 10 to the power 7 around. Okay. And as we know, wavelength, what is wavelength? This distance is actually the wavelength, right? Wavelength is the distance traveled by the wave during its one complete oscillation. This is your wavelength. So lambda is the wavelength. Wavelength is denoted by lambda and wave number is denoted by nu bar. So there is a certain relation between this wavelength and wave number, right? Now from the definition of nu bar, we can write nu bar, number of complete oscillations occur within 1 meter distance. So the one complete oscillation occurs within 1 by nu bar meter distance, right? Now from the definition of wavelength, we know that the distance traveled by the wave during its one complete oscillation is known as its wavelength. So and from this we found that one complete oscillation occurs within 1 by nu bar meter distance. So we can write simply this lambda. Lambda is nothing but 1 by nu bar, isn't it? One complete oscillation occurs within 1 by lambda bar meter distance, and the distance traveled by the wave during its one complete oscillation is known as wavelength. So simply this 1 by nu bar equal to lambda. It is the relation between wavelength and wave number. This relation will be necessary for the derivation of a Rydberg equation. Okay. Now it's the time for Rydberg equation. It explains the atomic spectrum of hydrogen atom. So firstly, we will derive the Rydberg equation and then we will find its very important applications, right? So firstly, we will derive the equation. If an electron jumps from N2 orbit to N1 orbit, then the energy emitted by the electron. Look at here. This N1 and N2, I have written N1 is less than N2. The value of N1 say is N equal to 2, but if the value of N1 will be N equal to 2, then the value of N2 will be 3, 4, 5, etc. Say if this one is the N1 orbit, then N2 may be this one or this one, etc. So the N1 will be the inner orbit and N2 will be the outer orbit. If an electron jumps from this N2 orbit to N1 orbit, that is the outer orbit to the inner orbit, it will emit some energy, and from Rydberg equation we will find the wave number and wavelength of the emitted energy, right? So we can write, if an electron jumps from N2 orbit, if an electron jumps from N2 orbit to N1 orbit, the energy emitted by the electron, we can write the energy as delta E. This delta E will be the energy difference between the N2 orbit and N1 orbit. So we can write energy of N2 orbit minus energy of N1 orbit. Okay. And as we know from the expression of energy, we can write this one is minus 2 pi square mz square e to the power 4 by n2 square into h square. I have just replaced this n by n2 for this case, and for E1 we can write this one is minus and this one is the negative sign of the energy expression. This is minus 2 pi square mz square e to the power 4 by n1 square into h square. Okay. There are many common terms except n1 and n2, all the terms are common. So we can take the common terms outside the bracket. This one is say 2 pi square m into z square e to the power 4 by h square into, this one becomes positive, this one becomes negative, so this is 1 by n1 square minus 1 by n2 square, right? Okay. And look at here, this is delta E, and we can write from Planck's equation this difference in energy. This one is delta E, and this energy difference will be definitely equal to h into nu. Nu is the frequency of the energy emitted. Okay. Now we can write nu equal to c by lambda. So this one will be equal to 2 pi square, I can write again, mz square e to the power 4 by h square into 1 by n1 square minus 1 by n2 square, right? So 1 by lambda, this 1 by lambda, this one is equal to, I can write this expression in this way, that 2 pi square m into e to the power 4 divided by c into h cube. This ch portion comes at the denominator, and into z square into 1 by n1 square minus 1 by n2 square. Okay. So this is, we have reached almost there. This is nu bar. This is our wave number. This one is represented by nu bar or 1 by lambda. This one equal to RH. This RH is known as Rydberg constant into z square into 1 by n1 square minus 1 by n2 square. So this is our famous Rydberg equation, this one. Right? Okay. Here the RH, this RH is known as the Rydberg constant. Now this RH is called Rydberg constant. RH is known as Rydberg constant, which is equal to 2 pi square m e to the power 4 by c into h cube, right? This one, the Rydberg constant RH. Okay. Now this Rydberg constant has two different values. Look, this 2 pi square m e to the power 4 by c h cube, all the terms are constant terms. M is the mass of the electron, E equal to charge of the electron, C is the velocity of light, and H is Planck's constant. So if we put all the values of these terms here, we will get the value of Rydberg constant. So it will be the theoretical value of the Rydberg constant RH. So its theoretical value, I can write here, theoretical value of Rydberg constant of RH, this one is equal to 109737 centimeter inverse. Look, the dimension of nu bar and RH are identical, and nu bar equal to 1 by lambda, because n1, n2, z are only values, it has no dimension. So the dimension of RH and 1 by lambda are equal, or the dimension of RH and nu bar are identical. Okay, so the theoretical value of RH and this one and from the spectroscopic data we get the experimental value of RH. The experimental value I can write here, the experimental value of RH, this one just differ a very little with the theoretical value. This one is 109,677 or 678 centimeter inverse. So this value is very important for our calculations. You will find this value of Rydberg constant, this one 109,678 centimeter inverse in the question paper of NEET, JEE or in different competitive exams. Okay, so this value is very important. Okay, now we will find another form of this Rydberg equation. If we multiply CH in both sides in either of these two equations, what will happen? I am multiplying both sides of this equation by C into H. Look, C into H into nu bar. This one equal to RH into C into H in Z square into 1 by N1 square minus 1 by N2 square, right? So this nu bar equal to 1 by lambda, so this is nothing but CH by lambda. This one is RH into CH into Z square into 1 by N1 square minus 1 by N2 square, right? And now this one is nothing but delta E. So the energy difference delta E is equal to Rydberg constant RH into C into H into Z square into 1 by N1 square minus 1 by N2 square, right? So this is another form of Rydberg equation. You can check the dimension of both sides of this equation. This RH into C into H gives the dimension of energy, right? So this is all about Rydberg equation, and using this equation we will explain the atomic spectrum of hydrogen atom, right? Now our next topic is atomic spectrum of hydrogen atom. In many books you will find the term spectra. You will find the term spectra, and in some other books you will find the term spectrum. So what is the difference between spectrum and spectra? So this is nothing but spectra is the plural number. This is the plural number and spectrum is the singular number. Okay, so don't get confused with these terms. Spectrum and spectra are same thing. Okay, now atomic spectrum or atomic spectra are of two types. One is absorption spectra and the second is emission spectra. We must have some basic idea about absorption spectrum and emission spectrum. So let's go on the screen to have some basic idea about absorption spectrum and emission spectrum. Okay, look, it is a discharge tube containing hydrogen gas. And when current is passed through this tube, the hydrogen gas absorbs some energy. When the current is stopped, the excited hydrogen atoms emit some energy, and after dispersion by the prism, you will get some lines in the visible region of the spectrum. It is red line, yellow line, blue line, violet line, etc. And this is actually emission spectrum because excited hydrogen atoms actually emit the energy, and that energy, the emitted energy, produces some lines in the visible region of the spectrum. What is about absorption spectrum? When sunlight is absorbed by the sodium chloride solution, some energy of the sunlight is absorbed by the sodium chloride solution, and after the absorption of some light by the sodium chloride solution, if this sunlight is dispersed by the prism, you will get some dark lines in the visible spectrum. So actually some wavelength or some frequency which corresponds to the energy which is absorbed by the sodium chloride solution produce the dark lines in the spectrum of visible light. So this is actually the difference between emission spectrum and absorption spectrum. In emission spectrum, you will get some colorful lines in the visible region because only the energy or the frequency corresponds to, so only the frequency which corresponds to the emitted energy are found in the spectrum, and in case of absorption spectrum, the frequency of the energies which are absorbed actually produces the dark lines in the visible spectrum, right? So it is the difference between emission spectrum and absorption spectrum. Now we will discuss about spectral series of hydrogen atom. Firstly, we have to know that how these spectral series have come, because hydrogen atom has only one electron, but actually a series of lines are produced. So how these series of lines are produced from one electron of hydrogen atom? Now we are discussing about the experiment by which the spectral series of lines are obtained, right? So this is a discharge tube where cathode and anode are present, and within this tube hydrogen gas is present. Hydrogen gas is present in this discharge tube, right? Okay. Now if we pass current through this tube, what will happen? Look what will happen. This is very important. So hydrogen gas is present there. So crores and billions and trillions of hydrogen molecules are present there in this tube. So these are hydrogen molecules, and when we will provide energy, firstly this hydrogen bond will be broken, and the energy required to break this hydrogen bond is known as bond dissociation energy. This is BDE. We will learn about this term in thermodynamics, in Born-Haber cycle of chemical bonding, and it has many applications. Okay, so bond dissociation energy is the energy required to break this hydrogen bond to produce hydrogen free radical. This is hydrogen free radical, or in simple language, this free radical is nothing but hydrogen atom. Okay. So hydrogen molecule, when hydrogen molecule is broken, two hydrogen atoms are produced, and for a hydrogen molecule this bond dissociation energy value is around this is around 434 kilojoule per mole. So to break 1 mole of hydrogen bond, we need 434 kilojoule of energy, right? If we produce more energy, now what will happen? Look, the electron present in the hydrogen atoms, firstly these electrons are present in the ground state, that is the first orbit, at the first orbit of hydrogen atom. And now if we produce further energy, what will happen? Definitely the excitation occurs. Excitation will occur. So the electron of the hydrogen atom will go to the outer orbits, and it will produce excited hydrogen atoms. It will produce excited hydrogen atoms. Okay, and this is very important. In the excited hydrogen atoms, the electrons are present in the higher orbits. Say this is first orbit, second, third, fourth, fifth, and so on. When the excitation occurs, the electron of the first orbit can go to the second orbit, can go to the third orbit, fourth, fifth, and to the further orbits. As I told earlier, there are crores and billions and trillions of molecules are there. When the molecules are broken, they produce billions and trillions of hydrogen atoms, and the electron of different atom will go to the different energy levels. Okay, and now what will happen? Look, now if we stop the energy source, if we stop the current, what will happen? Now de-excitation, actually de-excitation of the electrons will occur. That is, the electrons of higher orbit now come to the inner orbit. Electrons of the higher orbit now lose their energy, emit the energy to come back to the inner orbits, and this de-excitation can occur differently for different atoms. That is, look here. Say this is your first orbit, this is equal to n equal to 1, this is n equal to 2, 3, 4, 5th, 6th orbit. Okay, when the electrons of the excited state come back to the inner orbits, inner energy levels, what will happen? Now if the electron is present in the second orbit, it can come to the first orbit. From the third orbit, it can come to the first orbit. From the fourth orbit, it can come to the first orbit. From fifth orbit, it can come back to the ground state. From the sixth orbit, it can also come back to this state. Okay, so actually a series of lines can occur. Don't get confused, very important. Look at here very carefully. One hydrogen atom has only one electron, but there are crores and billions and trillions of hydrogen atoms are there, as I told earlier. So for different hydrogen atom, say this is the electron of one hydrogen atom, this is the electron of another hydrogen atom, this is the electron of third hydrogen atom, and when they come back, and importantly, all the hydrogen atoms are present in this charge tube. So when the electrons of different atoms come back to the original state or the ground state, or any of the inner state, a series of lines will occur. This is the series of lines. When the electrons will come from the third orbit to the second orbit, from the fourth to the second, from the fifth to the second, from the sixth to the second, this is another set of lines will occur. And these series of lines have different names after the name of the scientist who actually observed these lines, are known as the spectral series of lines. Okay, this is the idea of the production of the spectral series of lines. So actually this is an emission spectroscopy, right? Now we will find the Rydberg equation for different series of lines, right? These are the 6 spectral series found in the spectrum of hydrogen atom. We will discuss about this series one by one. First one is the Lyman series. I have written the Rydberg equation over there. For the Lyman series of lines, the wave number nu bar, this is equal to RH, Rydberg constant, into 1 by 1 square minus 1 by n square. So the value of n1 is 1 here, and the value of n2 is n here, is generally written as n. So the value of n is greater than 1, that is 2, 3, 4, 5, etc. positive whole number, right? And for the Balmer series, this n1 is 2 and this n2 is n, where the value of n is greater than 2, that is 3, 4, 5, etc. For Paschen series of lines, this wave number nu bar equal to RH into 1 by 3 square minus 1 by n square. That is, the value of n1 is 3 and the value of n2 is n. So n equal to 4, 5, 6, etc. For the bracket series of lines, the nu bar equal to RH into 1 by 4 square minus 1 by n square. The value of n is greater than 4. Next series is Font series. For it, the value of n1 is 5 and the value of n2 is n, where the value of n is greater than 5. And lastly, for Humphrey series, the value of N1 is 6 and the value of N2 is generally written as N, where N is 7. These are the 6 spectral series found in the spectrum of hydrogen atom. As you see in the image that when the electrons come from the orbits higher than the first orbit, from the second orbit, from the third orbit, from the fourth orbit, fifth and sixth and seventh orbit, these Lyman series of lines are obtained. Okay, and when the electrons come back from the third, fourth, fifth, sixth, seventh orbit to the second orbit, these Balmer series of lines are obtained. When the electrons come back from the fourth, fifth, sixth and seventh orbit, these Paschen series of lines are obtained. For bracket series, the electrons come back from the fifth, sixth or seventh orbit to the fourth orbit. For Fermi series, electrons come back from the sixth or seventh orbit to the fifth orbit, and for Humphreys series, electrons come back to the seventh orbit. Now there are 2 or 3 important points to note that as we discussed in the second topic of today's video, that the energy difference between first orbit and second orbit is the largest. So when the electron comes back to the second, third, fourth, fifth or further orbit to the first orbit, the energy difference is highest. So this Lyman series of lines actually occurs in the UV region. It occurs in the UV region. As you can see in the image, this series of lines occurs in the UV region, and this series of lines, that is Balmer series of lines, occurs in the visible region. This is very important. Only the Balmer series of lines occurs in the visible region of electromagnetic radiation. Okay, and this Paschen series of lines occurs in the IR region. Definitely the energy of UV is highest, then visible, then IR. So these lines occurs in the IR region, and other lines, that is bracket, Fund and Humphreys series of lines, occurs in the far IR region. These are occurs in the far IR region. Far IR, this one far IR, and Humphreys series of course occurs in the far IR region. Okay, we can see only the Balmer series of lines in our open eye which occurs in the visible region. Okay, now there is a very important trick to memorize these series of lines. So this memorization is very important, because as you can see that for Lyman series the value of N1 is 1, for Balmer series it is 2, for Paschen series it is 3, for bracket series it is 4, for Fund series it is 5, and for Humphreys series it is 6. So if we memorize this name, the name of this series sequentially, then of course we can find the value of N1 for that particular series. So it is very important to memorize this series in the sequential manner. So now come to the trick. In the word Lyman there are 5 letters. Okay, in the letter Balmer there are 6 letters. In the letter Paschen there is 7 letters. In the letter bracket it is 8 letters. In the name of Fund there are 5 letters, and in the letter Humphreys there are 9 letters. Okay, so it is 5, 6, 7, 8, 9. So of course the Fund is the exception. Lyman is 1, so it contains 5 letters. Balmer is 2, so it is 6 letters. For Paschen it is 7 letters. Bracket is 8 letters word. Bracket is a 8 letter word, and Humphreys is a 9 letter word. सब लोग रूल फॉलो करेंगे तो एक ही तो एक्सेप्शन हो ही जाएगा ना. ओके, सो राइट, सो फंड इज एक्सेप्शन. ओके, for the so fund is the exception. For the other series of lines it is 5, 6, 7, 8 and 9. Right, it is the trick to memorize this series sequentially. Now for us this Balmer series of lines is the most important, because this series of lines we find in the visible region of electromagnetic radiation series. Okay, In the Balmer series of lines, actually we can see only 4 lines in the visible region. They are H alpha, H beta, H gamma and H delta. Now we will go on the screen to see the 4 lines of Balmer series. Okay. Now look, these are the 4 lines. This is H alpha, this is H beta, this is H gamma and this is H delta. These 4 lines we find in the visible region of Balmer series. Look, this H alpha line occurs in the red region. It is red in color. This H beta line, this is bluish green in color. This H gamma line is blue in color, and H delta is violet in color. As we go from the red end to violet end, what will happen? The frequency will increase and the wavelength will decrease. So the wavelength of red line is maximum. So actually this H alpha line occurs due to the electronic transition from third orbit to the second orbit, isn't it? Because the energy difference between third orbit and second orbit is minimum, so its wavelength will be maximum. So this H alpha line occurs due to the transition from third orbit to second orbit. This H beta line is of course obtained due to the transition from fourth orbit to the second orbit. This H gamma line is obtained for the electronic transition from fifth orbit to second orbit, and this H delta line is obtained from the electronic transition from sixth orbit to the second orbit. So this is a very important concept. This question has been set several times in many competitive exams. You can find it in JEE Mains, NEET in several times. Okay. So these are the 4 lines that are found in the visible region of electromagnetic radiation, right? Now we have come to the 5th topic of today's session. It is the advantages of Bohr's atomic model. Here are the advantages of Bohr's atomic model, which is written in the note form. It will be useful for your board exam, and of course the concepts are important for competitive exams also. First one, the advantages of Bohr's atomic model. First one is the stability of the atom. Of course, the defects of Rutherford's atomic model was that Rutherford's model can't explain the stability of an atom, but Bohr's model can at least explain the stability of an atom. Then the line spectrum of hydrogen and hydrogen-like systems can be explained by Bohr's atomic model. Then the radius of first orbit of hydrogen atom, that is obtained from Bohr's model. The value is 0.529 angstrom, we know. We can find the idea of principal quantum number from Bohr's atomic model. The energy of an electron can be calculated from Bohr's atomic theory. And lastly, the Rydberg constant and its mathematical value can be obtained from the energy expression of Bohr's atomic model. And the limitations of Bohr's atomic model are arranged as follows. Atomic spectra, which is explained by Bohr's theory, is applicable to a single electron system only. It is not applicable for multi-electronic system. Next, Bohr's theory can't give us explanation of the splitting of spectral lines under the influence of magnetic field, that is Riemann effect, and under the influence of electric field, that is Stark effect. Bohr's can't give any idea about the Riemann effect and the Stark effect. The third point is Bohr's atomic model is two-dimensional. It fails to give us any sort of idea about the three-dimensional electronic model of an atom. Number 4 point, de Broglie actually introduced the concept of dual nature of electron. Electron can have both the particle and the wave nature, but Bohr's atomic model is based on only the particle nature of an electron. It can't give any idea about the wave nature of the electron. And number 5th point, Bohr's atomic model directly contradicts Heisenberg's uncertainty principle. In the next video, we will discuss about these two very important theories, that are de Broglie hypothesis and Heisenberg's uncertainty principle. Okay. So guys, that's it from this video. In the next video, we will discuss about de Broglie equation and Heisenberg uncertainty principle. So take care, keep learning, enjoy your learning. We will meet in the next video. Till then, bye bye.